So welcome to section 12.5, and looking at my notes, I realized that I actually missed the last page or two on 12.3, intermolecular forces. So let's start there, and part of it is a summary of intermolecular forces. But part of it is also this last force that the textbook is calling ion dipole forces. And the reason I forgot about this was because you can't actually have ion dipole force for a pure chemical. Hydrogen bonding dipole, and London dispersion, or what do we call them? LDFs? They get called slightly different in everything. They call them just dispersion forces. Those all exist for pure chemicals, and that's the way we talked about them. For example, with water, we talked about how one water molecule can be hydrogen bonded to another water molecule. But it turns out that if a different chemical, like HF, also has an HO, HN, or HF bond, we can also have a hydrogen bonding between water and HF. So it works for pure chemicals, holding them together in the liquid or the solid phase, but also works for mixtures. But we didn't really talk about mixtures all that much, and now we have to talk about them with ion dipole. So with water, again, we've talked a lot about it, how it's got that partial positive on one side and the partial negative on the other. And it turns out that helps water dissolve ions. So here's a classic ionic compound, sodium chloride. And the way that water dissolves sodium chloride, you probably know that sodium chloride is alternating chlorides and sodium ions in all three dimensions. I'll just show two dimensions here. So it's got some large chlorides interspersed with some smaller sodium ions. Cations are smaller, anions are larger. And what water does is it goes in and it grabs one ion at a time. And since that was a sodium, it's going to orient the oxygen side, the negative side, towards the sodium, towards the positive sodium. And they're showing 6 here, and I think 6 might be right, but sometimes it's 8, sometimes it's 10, 12. These are called solvation shells, a number of ions that are very close to the cation and holding it in solution, sort of supporting it. This is why every little piece of salt water tastes the same, is because the ions are being surrounded by the water. And if enough of the ions got back together, well, they would fall back out as a crystal. And then water, again, has that partial positive side, the hydrogen. And so those hydrogens are going to orient close to the negative. So again, opposites attract, positives attract negatives, and vice versa. And so now chloride's got 6 water molecules in a solvation shell holding the chloride in solution. And it turns out that the ion dipole force is relatively strong. They're showing its range is at least as strong as hydrogen bonds, but can go up even stronger than that. So here are our forces. Here are our strengths. They're putting numbers on them, the types of numbers that it takes to break these intermolecular forces. And again, you should notice that these are much, much weaker than breaking covalent bonds, although some of these ion dipole forces are sort of in the range of breaking covalent bonds. But the intermolecular forces are much weaker. So you break intermolecular forces first and force chemicals into the liquid or the gas phase. And then if you keep applying more energy, then you start ripping covalent bonds apart. And then here's a really interesting example of some of the intermolecular forces. A while ago, I was teaching some courses. I was teaching a lot of OChem lab and biochem lab. And I realized at the beginning of almost every lecture, I was talking at the lab lectures, I was talking about intermolecular forces. The whys of all of those really interesting questions that we deal with in biochemistry and biology. The why does this medicine bind to this protein? Why does DNA stick together? Why does RNA stick to DNA? Is because of intermolecular forces. So here are small parts of the DNA bases: thiamine, which you might know as T base, A, C, and G. And everybody learns from a pretty early age that G's pairs with C's and A's pair with T's. Now that you are experts on Lewis structures and shapes and polarity and finally intermolecular forces, now we can see why that is. A has an NH and an N with a lone pair. And thiamine, has an O, which is negative, a CO. So that's got a dipole moment right there. And it's got its own NH here. And so they've got these perfectly matched hydrogen bonds just the right way, kind of like a key into a lock. You got to have grooves in just the right place to turn the lock. Same thing with A and T. They got to have these H bonds perfectly lined up so that you get these two H bonds. These down here are a little bit too far away. They're not oriented to be interacting. Plus, this is a CH, so it's not even that polar. So just two hydrogen bonds. And then G's with C's pair up because of three hydrogen bonds. And you can see those there with the dotted lines. And again, you got a lot of NHs, and you got those carbonyls with the oxygen having a delta minus. And then also the nitrogen having a delta minus there because of the CN dipole moment. But it's got three hydrogen bonds. And something that's kind of cool about this is it lets you predict how well pieces of DNA stick to each other. So if, let's say you had a piece of DNA like this, well, first, you know that every A must pair with the T and vice versa, and G's must pair with C's and vice versa. And because of this, we know that we can actually go and calculate at what temperature they would fall apart from each other in solution. But this one would be pretty low, like even under room temperature, 5 little bases fall apart. But once you get up to like 20 or so bases at room temperature, they would stick together. But if you heat it above the temperature, then they would fall apart. And the G's and C's hold the DNA a little bit more than the A's and T's because of that extra hydrogen bond. And so that's looking at one base at a time. And again, in every one of our cells, we have 6 billion base pairs of DNA all stuck together in a double helix. So here's a much longer strand of DNA. Here's the original strand of double-stranded DNA. And again, you see A's and T's. And look, they're being very specific. There's 2 lines between A's and T's, and 3 lines between G's and C's. So they're all paired up in a very particular order. And then they're not showing it, but there's this huge protein complex with a lot of different proteins. It's sort of unwinding the DNA on the front. And then in the back, these other proteins are kind of synthesizing new strands. So in red, they're showing the new strands come in. And this is how cells divide, where each cell gets an exact duplicate of the DNA. Because as it unwinds, the protein sees an A there and knows, oh, I'm going to pair it up with the T. Oh, there's a T here, I'm going to put an A. There's a C, it's a G. G, C. And so on and so forth. So that the 2 new strands are identical and matched the old strand. And again, it's all due to hydrogen bonding, intermolecular forces. If these were covalent bonds, like I've sort of drawn here, you couldn't just unwind it with a protein. It would take way too much energy to rip one strand apart and break those covalent bonds. And if you did, you might accidentally break other covalent bonds in DNA. So it's super important that on the one hand, it's strong enough to stay together at your body's temperature, 37 Celsius. But on the other hand, it's weak enough that it can be kind of ripped open using just the energy from ATP to make new strands. So that's sort of intermolecular forces in action. The higher up you go in your science courses, the more intermolecular forces you'll see. And now we get to dive into 12.5, vaporization and vapor pressure a little bit. So we learned about intermolecular forces and what's holding chemicals together in the liquid and solid phase. And now we're going to talk a little bit more about vaporization and vapor pressure. Vaporization is boiling, and vapor pressure is when you have a liquid and some of them escape, some of them evaporate and create a little bit of pressure. If it's an open container, it doesn't really change the pressure of the atmosphere because it just keeps pushing against the atmosphere. And the atmosphere is so enormous, it just stays at 1 atmosphere. But if it's in a closed container, those chemicals will keep evaporating until a certain pressure is reached, until that vapor pressure is reached. One thing that everybody's got to know that goes through a general chemistry course is that boiling / evaporation is endothermic. And at first that feels a little counterintuitive because we know boiling, when we think of boiling, we think of water boiling. And we know water boiling is hot. It's hotter than room temperature. So we feel like maybe it's the opposite of this. Because if we were to go over and touch it, we would absorb heat from the pot. But from the chemicals point of view, to go from the liquid phase to the gas phase, it's endothermic. That those chemicals have to grab some extra heat from somewhere, and they leave with the heat. So here it is in chemical reaction. H2O in the liquid phase can go to H2 in the gas phase. Delta H vaporization, again, that's the change in enthalpy. Are you saying the word enthalpy every time you see this H? But then are you thinking heat? So say enthalpy, but think heat. Enthalpy is just a fancy version of heat for chemists at constant pressure. Notice that it's positive. And again, remember, endothermic means a positive delta H. And now you might be thinking, well, I remember that endothermic meant pulling heat in and that it would feel cool. And we're going to see, actually, I should probably just say it now. Evaporation is endothermic. From the chemicals perspective, they're taking heat. From our perspective, if you put your hands on something that's endothermic, it pulls heat out of your hands. And the same thing is true here. So if you got your arm and you got some water on there and you're working really hard, maybe it's a hot day, hopefully it's not too humid, there's not too much water vapor in the air, the water molecules, they can take some of that heat from your body and they evaporate and they leave with that heat. And again, to your body, it feels cool, but to the water molecule, it took the heat away. It's got more energy than it ever did when it was in the liquid phase because now it's in the gas phase. And this kind of brings up another thing that maybe I want to spend a minute on is you always have what we call the system and you always have what you call the surroundings. And again, you define the system and you define the surroundings. And here we're defining the system as the water and the surroundings as maybe my arm that the sweat is evaporating off of. And the heat is going from my arm to the water, and the water leaves with the heat, it evaporates. And from the water's point of view, it's endothermic. From my arm's point of view, it's actually exothermic. If you were to reverse this, if you were to call your arm the system and the water the surroundings, then the system would be exo, right? So you define what's the system and the surroundings. The process, that part doesn't change. So if you call your arm the system, the chemicals on the surface of your skin where the water is evaporating from, and the water, the surroundings, heat is still going from your arm to the surroundings. From your arm to the water, but now the surroundings are endo. They're absorbing heat. And your arm is still exo, the system. So I'm a little worried that showing the reverse of this kind of confused everybody. But the point I was trying to make, if one thing gives up heat, another thing absorbs the heat. If I give you $20, you are plus $20, but I am minus $20. Same thing for heat. If the water absorbs the heat, something had to give that heat up. And so here we got an interesting picture on some sort of chemical in the liquid phase, and they're showing the difference between being part of the bulk versus being on the surface. And this is why there is a surface, is because the chemicals that are on the surface, remember, if we're picturing chemicals sort of in this molecular dance when they're in the liquid phase. They're moving around, they're colliding, they're rotating, they're vibrating. And when a chemical finds itself on the surface, this one only has 4 other intermolecular forces. If it's water, maybe those are H bonds. If it's just polar, like acetone, maybe they're dipole-dipole. If it's not polar, like hexane and gasoline, maybe these are just LDFs that we're showing. So it's only intermolecular, it's only bonded with intermolecular forces to 4 others, while the bulk one is stuck to 6 other molecules. And so there's a real driving force for the ones on the surface to find their way back into the middle, because it will maximize intermolecular forces. It will release a little bit of energy. It's a lot more stable for the chemical. But you'll probably recognize that as soon as this one finds its way into the bulk, then another one will have to take its place as the surface. So this is kind of what's happening in solids and liquids. They are their constant volume because they're technically, it's more energetically favorable for the ones on the surface to find their way back into the bulk. And that's just kind of happening over and over again. And there's a really cool picture that demonstrates this really clearly. If you look up water in outer space, it might even be in our textbook somewhere. Water makes a perfect sphere in outer space where gravity is not pulling it into droplets. And this is, again, all those individual water molecules kind of in this crazy dance, trying to find their way back into the bulk over and over and over again. And it gives rise to things like surface tension and viscosity, which you could read about in 12.6 if you wanted to. No, maybe it's 12. I think it's in 12.4 actually. Okay, so liquid water turns to gaseous water. It takes, we all know boiling, this is the boiling point, 100 degrees Celsius. It takes 40.7 kilojoules per mole, and that's a lot. If we come back up here, that's actually sort of at the high end of hydrogen bonding, and that's because, again, water molecules are so small and so polar. It takes a lot of energy to evaporate them, which actually makes it a really good molecule to use for sweat, because such a small amount of it takes so much heat with it whenever it goes. If you sweat out 18 grams of water, you just lost 40.7 kilojoules of heat that would otherwise be warming your molecules above 37, right? You guys know our bodies have to stay at 37 degrees Celsius. And when we're working really hard, we're burning that energy, a lot of it's getting converted to heat, and our bodies would, without sweating, go up above 37. Now you got a lot of problems with proteins misfolding and a bunch of other things happening. So sweating is really important part of keeping your body's temperature the same. But chemicals boil at different temperatures. We got some, I wanted to have a diagram with some vapor pressures, but it didn't look like I could make it in. And they have different enthalpies of vaporization. The picture that I was hoping to have there, the table is on page 514, and we'll reference that here in a second. And the vapor pressures is on page 517. Oh, here they are. Oh, well, just the vapor pressure. So look, here's diethyl ether. It boils at 34.6 and has a vapor pressure of 760. We'll talk a little bit more about vapor pressure here in a second. Coming back up to the table, maybe, it's a different table. Okay. The table on page 514, it says diethyl ether has a delta H of vaporization of 26.5 kilojoules per mole. So we would look that up. Change in enthalpy of vaporization, 26.5 kilojoules. You could write an equation if you want, if that helps you sort of sort this out here. We've got diethyl ether. It's giving us a formula. Heat of vaporization is always from the liquid to the gas phase. And we see right there, it's endothermic, of course, is 26.5 kilojoules. That always means per mole of the reaction. So you can't just do this for one diethyl ether molecule. You might be wondering what this looks like. CH3, CH2, oxygen, CH2, CH3. Kind of an interesting chemical. It's pretty flammable. It's got a pretty strong smell, and this is usually the chemical. Sometimes it's just called ether, and a lot of detective stories use it where the bad guy puts it on like a cloth and then puts it over someone's face, and they inhale it a little bit, and then they faint, and then they pull it away, hopefully in time not to suffocate them, and then they wake up a little bit later. Maybe at one point it was used a lot. I don't know if a lot of people are using that for this. Hopefully not. It says calculate the mass of diethyl ether that can be vaporized at its boiling point with 155 kilojoules of heat. So we're putting in 155 kilojoules of heat, and we want to know how much diethyl ether evaporates. So the obvious place to start here is with the energy that's given. And then this is 26.5 kilojoules for every 1 mole. It's right there. A lot of times we don't see that per as a 1, but that's what it means. And this happens all the time. So say someone tells you that they're driving 45 miles per hour. We know that MPH means miles per hour. We sometimes forget to put that 1 in there. That means 1 hour later, we have gone 45 miles. Same thing here. It takes 26.5 kilojoules to evaporate 1 mole of diethyl ether. So we'll put the kilojoules on the bottom to make sure those units go away to get moles. So 155 divided by 26.5, and we get 5.85. Maybe I'll carry one more sig fig. Kilojoules go away, moles pop in. Carry one more sig fig so I don't round too early. It didn't ask for moles, though. It asked for mass. But again, hopefully you're feeling really comfortable on the grams to moles calculation. You got moles, you want grams, or vice versa. You're using the periodic table. So we got to add these up. So 4 carbons is going to be 48.04. 10 hydrogens is going to be 10.08. And 1 oxygen is 16. So this is 74.12. So every 1 mole of diethyl ether is 74.12 grams. And then so we just multiply across. 74.12 times 5.849. And so we get 433.5 with only 3 sig figs everywhere. Technically, we should call this 434 grams of diethyl ether would have evaporated. I've actually done this before, sort of on accident. Because it boils, its enthalpy of vaporization is lower than water, and it boils at a lower temperature. Its vapor pressure is a lot higher. You leave a beaker of ether out, and you come back an hour later, and it has evaporated away. It's just gone. It's in the gas phase. And if you come back, as soon as that happens, the beaker will be very cool because it took all that energy out of there. There's a really cool explanation in the book for why things feel a little bit cool. And so here is 2 different energy diagrams. This is an interesting picture. So it's talking about the kinetic energy of the molecules, and they've got 2 different temperatures. So at the low temperature. So imagine that you got your beaker of diethyl ether. Some of the chemicals have this energy. So we're looking at the blue curve. A little bit more of the chemicals have this energy, a little bit more have this energy. This is because when you look in that beaker, some of them might be perfectly still after a collision. They lost all their kinetic energy. But then after a collision, they should be the same size since they're all the same chemical. After a collision, one might be racing away. So that would be over here. This is really high kinetic energy. It's moving really fast. It's vibrating a lot, or it's rotating really, really quickly. This is sort of the middle the median. This is the most likely one. So if you looked at 100,000 of these molecules, all of them have sort of a slightly different kinetic energy. But then if you were to try to group them together and say, oh, well, this kinetic energy is sort of the average or the most common. You counted them up. So it says fraction here, so maybe 1% of them had this energy, and then like 25% had that energy, in this little bin right here, and so on and so forth. So under the curve, you got a total of 100%. But what you're seeing is that some of the chemicals have low energy, some have high energies, and most of them have sort of a common middle energy. And this is a standard curve. What they're saying here is that there's some minimum that's needed for a surface molecule to escape. So if we come back up here, maybe this surface molecule just has a little energy. It's not enough to escape. It tries to escape, but then it gets pulled back in by its intermolecular forces. But then after a collision, this one has a ton of energy. It's now up here. It's got enough energy and it's at the surface, so it escapes. And so what happens is 5 minutes later, this percentage of molecules under the curve, they both had enough energy and they reached the surface, so they left. And so 5 minutes later, look at what's left in the beaker. The 90% of molecules with less energy. So the vapor is constantly carrying away the most energetic molecules. So over time, what's left is molecules with less energy. So that's why it feels a little cooler over time. Of course, during this process, it's getting re-warmed up by the room. So it's not like it keeps getting cooler and cooler and cooler. There's this sort of equilibrium temperature that it reaches. Some amount of heat is getting released to the evaporation. Some amount of heat is getting replenished by the room. If you then warm up those beaker of chemicals, each individual chemical might get a little bit more energy. So this one's moving a little faster, that one's moving a little bit faster. Every single one's moving a little bit faster. Yeah, there's still some with really low energy, but there's fewer of them. Yes, there's a lot with that same middle energy that we had before, but quite a bit fewer. The middle has moved up quite a bit. And what's most important here is that a larger percentage of the molecules have enough energy to evaporate. So if instead of leaving that ether at room temperature 20 Celsius, if you leave it in a hot day or you put it in your hand, it's now 37 Celsius, it's going to evaporate a lot quicker because more molecules have enough energy to escape. This is our first introduction to this idea of equilibrium, that there's some sort of median place that chemicals get where technically they're still moving, but to look on it macroscopically, it is sort of done reacting. So let me explain. So here's water in a closed container. So you put a little bit of water in a Erlenmeyer and then you cap it. At first, what happens is a little evaporation. So some evaporation. The water is filling up that space a little bit. The pressure goes up a little bit. Every time a water molecule enters the gas phase, the pressure has to go up a little bit. So it's not a ton isn't going to evaporate because it's closed, but some will. And then a little bit more evaporates, but some are starting to condense. So what you'll see here is 3 arrows up, 3 evaporated, 3 evaporated, and 2 recondensed. So some are evaporating, some are recondensing, but still we're getting more evaporation than not. So some evaporation, some condensation, but ultimately this is a net evaporation. And you've probably seen a problem like this at some point, right? You got that water tank where it's got a hole in it and it's losing a gallon a minute, but it's being filled up at 2 gallons a minute. When will it completely fill up? It's kind of the same thing that's happening here. Some is evaporating, some is condensing. When will it sort of reach equilibrium. And that's what we got over here, dynamic equilibrium. This is when the rate of evaporation equals the rate of condensation. And again, they're showing 3 evaporate and 3 condense. And so the pressure was still increasing here, but now it's just at constant pressure. Every time 10 evaporate, 10 more condense. And they might condense somewhere else. You might get a water droplet up here on the neck of the beaker. The longer you let it sit, the more water droplets you'll find. But ultimately, the same number are in the gas phase. The same number are in the liquid phase. And so, look, they're showing at the very beginning, there was a certain rate of evaporation, and it was pretty constant. It just kept evaporating. And at first, condensation, there was none. There wasn't any water molecules in the gas phase, right? There's no water molecules here to condense. So at the beginning, the rate was 0. But over time, as more water molecules go into the gas phase, more start to condense. So it starts to speed up a little bit. At some point, though, after B, the 2 rates are equal, and there's no net change. So dynamic equilibrium is achieved when the rates are equal. Dynamic equilibrium means that there's no macroscopic change. At the beginning here, if you looked at it and then you come back a couple hours later, again, you might see some water droplets. But then once it reaches this, and then another thing you could do is maybe like on a scale, you could like weigh the water. There would be a little bit less water in the bulk here. You let those water molecules escape, you weigh the rest, you're like, oh, there's a little bit less. It would be hard to get a scale, I think, sensitive enough to measure that, but those water molecules are in the gas phase and they would leave if you open the container and tried to weigh the liquid inside. And then finally, this last one is dynamic equilibrium. There's no macroscopic change. If you look at it and then you come back 10 hours later and you look at it again, it will look identical no matter how you look at it. But the reason we call it dynamic is because if you were able to see the individual molecules, again, you would see this really crazy energetic dance where some evaporating, some condensing. But from the macroscopic level, it doesn't look like anything's really happening. And so what we're doing right now is actually giving a really good preview to the rest of the semester. This is equilibrium is the topic of chapters 16, 17, and 18. Then we start to learn why a little bit more in 19. Then we apply it to batteries in 20. So the more time we spend with these concepts, the less time we have to spend on the concepts when we get to those chapters, and the more time we can spend on the calculations. Here, we're letting some liquids evaporate, fill up the container, achieve a certain pressure, but then it's in a piston, so we change the volume. And whenever we change the volume, we change the pressure. And then what we notice is that the system responds by either evaporating to fill up the space or by condensing to empty the space to get back to that same pressure. So these will always be constant pressure. And here's another really big idea. We'll end up calling it Le Chatelier's principle, but chemical systems, when disturbed, will move in a direction to re-achieve equilibrium. Okay, so here it's at equilibrium. And again, they're being very specific about the arrows. They're showing them equal, showing some amount of evaporation, some amount of condensation. There would be some pressure here, some vapor pressure. It looks to me like maybe butane. It probably says specifically here. It's like butane or pentane or hexane, something that's a liquid but still evaporates pretty easily. So the vapor pressure is sort of constant. Some amount is in the gas phase. If you then expand the container, the pressure goes down, and all of a sudden the liquid, sort of noticing that. I talk about chemicals as if they can pay attention and notice and have feelings a lot, just to make it a little bit more interesting. So you can kind of put ourselves in their shoes. But again, they don't have feelings. They can't see or observe anything. But that pressure goes down, and now the rate of evaporation stays the same, but the rate of condensation decreases. So again, they're showing that arrow go down a little bit because there's more room between the molecules. When they collide, there isn't as much driving force for them to reform a droplet and re-enter the liquid phase. So when the volume is increased, pressure falls, more gas vaporizes until the pressure is restored. So if you wait long enough, again, you'll see this. Now the rate of condensation will slowly inch back up until they're the same, and you have the same concentration of gas molecules, and then vice versa. If you compress it, you speed up condensation. What you're doing is if you measure the concentration of chemicals in the gas phase, when you change the volume, when you decrease the volume, you're increasing that concentration. And again, you're speeding up condensation. And so that will happen because the pressure is too high until the pressure reaches that constant. So that's kind of an interesting phenomenon for gas evaporating. Here's vapor pressure increasing with increasing temperature. So you got temperature on the X, it's increasing. We got between water freezing and and boiling, 100 Celsius, and vapor pressure, 760. This is in torr or millimeters of mercury. Those are the same units. 760 millimeters of mercury or torr is 1 atmosphere. That's room pressure. So most of the time, we would really only care about that one pressure. We wouldn't really care about the other pressures. But what this is showing is that, so let's say you're at room temperature, you're here, and you're at 1 atmosphere. Well, water has some vapor pressure. That would be 100. It looks like to be around 10 or so. It's 10 to 20. That's the pressure above the water of the water vapor. And that's why it's pretty slow to evaporate. You have to wait a couple days for a little cup or dish of water to completely evaporate. Oh, another thing that we could say is that if you increase the surface area, you increase the likelihood that a molecule will have enough energy to evaporate. Because up here, when it was pretty thick and you only had some at the surface, if this one had enough energy, but it was in the bulk and it was so far down, it wasn't going to evaporate. It was going to collide a bunch more. So it was going to stay as part of the bulk longer. But if you pour it out, like you pour a beaker out on the floor, it's going to evaporate in a couple of hours because you've got a lot more surface area. Now, every time a molecule has enough energy to evaporate, it does and carries that heat away with it. And so what you see is that vapor pressure increases with increasing temperature. So eventually, at 40, it's now around maybe 50. At 60 Celsius, the vapor pressure is around 100, so on and so forth. You warm water up to 100 degrees Celsius. Now the vapor pressure is 760 millimeters of mercury, or 1 atmosphere. Boiling is achieved when the vapor pressure is equal to the atmospheric pressure, which near sea level on Earth is 1 atmosphere. So again, if we were on a different planet, the pressure would be very different. Water wouldn't boil at 100 Celsius anymore. If the pressure was higher, it would boil at a much higher temperature. The boiling point, every molecule on average has enough energy to enter the gas phase. So if you come up here, this one, if this is water and you heat it up to 100 Celsius, every single molecule now has enough energy to enter the gas phase. So this one and this one and this one might make a little water bubble. And that's what the bubbles are. They're usually forming on the surfaces of your pot of boiling water. And then that bubble of water has such a low density that it rises up out of the water and escapes and joins the atmosphere. But notice different liquids will boil at different temperatures. Diethyl ether that we thought about a little bit earlier, it's got a very high vapor pressure. So even at room temperature, it's got the vapor pressure close to 400 millimeters of mercury. That's why it's got such a strong smell. So much of it is evaporating. And you heat it up just a little bit to 34.6. This is actually lower than your body temperature. So you put a little bit of diethyl ether in your hand. You shouldn't, because you might absorb a little bit of it. It's not good for you. But if you put a little bit of it in your hand is 37. And so it will start boiling in your hand. It will feel cool to you because it's boiling at less than your skin temperature, and it's taking the heat away with it. So it might not boil for very long, but it will evaporate very, very quickly. Another interesting thing here is that you might notice that water actually doesn't ever really go to zero, even at zero. This is frostbite. So if you put like a bag of veggies in your freezer and you leave it there for a couple months and you open it up, there's all that ice in there. Where did that ice come from? I used to think that it came from the freezer itself. The freezer would condense the water, but most of it was inside the bag. That's not true. Bags are airtight. That water used to be inside the veggies, but even at the temperature inside your freezer, a little bit of the water is evaporating. It's going from the solid phase to the gas phase. It's got a vapor pressure even below its melting point. But then it refreezes inside the bag somewhere else outside the veggies. So remember this, vapor pressure increases with increasing temperature, and the boiling point is achieved when the vapor pressure is equal to the atmospheric pressure. So now, I guess I didn't have really a picture of water open. We had the water closed, but now we're heating it up. It starts with a low vapor pressure. It's still evaporating a little, and we increase the temperature. More of it starts to evaporate. We increase a little bit more and more starts to evaporate. But when we think about water boiling and evaporating, especially when we're doing it in our kitchens, we totally forget about the atmosphere. The atmosphere has all of those gas molecules, the N2, the O2, the argon, the CO2, pushing down on everything, especially near sea level. It's got this one atmosphere. And so if you heat it up so that the vapor pressure is also one atmosphere, now you've got boiling. On average, every single molecule has enough energy to enter the gas phase. That's not a great curve. I think it looks something like this. That's not great, but the average is right here. The average molecule has enough energy to join the gas phase. So here's some interesting things on pressure and boiling point of water. So here you are at sea level. We're pretty close to that too. The pressure is very close to 1 atmosphere. And the boiling point is 100. If you go up a mile high, I actually grew up at a mile high, Southern California in the mountains. So the pressure is very close to 0.83. Now water is only boiling at 94. So you crank it up, the oven as hot as it'll go. That pot of boiling water, as soon as it starts to boil, it's at 94. And that's another thing that we have to remember. Because the boiling chemical is taking energy with it, boiling point is constant. So that's another fact to know here. If you see a pot of boiling water at sea level, it is 100 Celsius. You can actually set your thermometer to it, right? If you're trying to make a new thermometer and you're trying to figure out where is 100 Celsius, stick it in a pot of boiling water and let it sit there for a minute, and it will be at 100 Celsius. But if you're at a mile high, it's now at 94. This is why there's those extra directions on like brownies and maybe even pasta, some pasta. is because things are not cooking at the same temperature. So if you put dried pasta in boiling water and it says, 9 to 11 minutes, they're assuming sea level. But up in the mountains, it's only 94. It's not getting as much heat. You're not sort of almost dissolving the pasta, but then stopping before it completely dissolves. You're not rehydrating the pasta as fast. So you pull it out at 11 minutes, it'll be crunchy. So you got to let it go for a lot longer. And the higher up you go, the longer you got to let it cook, because the boiling point is lower and lower at higher and higher elevations. And the boiling point is constant. It doesn't matter how hot the flame is underneath it. Things are boiling. It's all dependent on the pressure. If you were to take this into Death Valley, there's more pressure. And so it gets to 100 and it's still evaporating. You got to heat it beyond 100 to match that pressure down in Death Valley. Finally, Mount Everest, things are boiling at 78. You're never going to cook your pasta at 78. And so that, I believe, is 12.5. I hope you're feeling more comfortable in using vapor pressure. What are the concepts of vapor pressure and dynamic equilibrium and evaporation and boiling? And then this is a cool graph that we can apply to every collection of molecules. They have some energy, but it's not every single molecule has the same energy. Some have low, some have highs. There's a lot that have sort of a middle amount, and they're constantly exchanging it through collisions. And then there's one set of calculations using that delta H of vaporization to convert between energy and mass. Quite often you might have to do this the other way around. 434 grams of diethyl ether evaporated. How much energy did it take with it? You'd have to go the other way around. You'd have to do a gram to mole conversion and then use that heat of vaporization.